Swayam Prabha. Digital India. Educated India.
becomes half ln Z3 over Z2, and finally gamma L becomes half ln RL over Z0. Okay, if we go back to these equations, see here, say I want to simplify this equation. So now in terms of these new gamma 0 values that I have written, I can write this as, so this equation, the first equation, I can write it like this: half ln Z1 upon Z0 is equal to 2 raised to minus 2 to C0 gamma L, which is equal to 1 by 4 into half ln RL upon Z0. Now this and this cancels. So from here we get Z1 is equal to Z0 RL upon Z0 raised to 1 by 4. Fine. Let's take this equation. So here we had ln, and this, go back to that equation. Okay, so from this equation, this gamma 1, I can write it like half ln Z2 upon Z1 is equal to 2 raised to minus 2 to C1 gamma L, which is equal to half into half ln RL by Z0. So again this half cancels, and we have Z2 equal to Z1 RL upon Z0 raised to power half. Now from these two equations, okay, this equation and this equation, we can get the values of Z1 and Z2. But we want to check whether we have got consistent solution. So let us consider this equation also. So this equation is that gamma 2, so in place of gamma 2 I substitute half ln Z3 upon Z2, and then this expression becomes 2 raised to minus 2 to C2 gamma L, which is equal to 1 by 4 into half ln RL upon Z0. This cancels. So from this we have the expression Z3 is equal to Z2 RL upon Z0 raised to power 4. Now suppose okay, so in order for my all three equations to give consistent solution, the value, if I substitute the value of Z2 that I obtained from this equation and put it here, then the left hand side and right hand side should match. Let us see whether that is happening or not. So I substitute this value of Z2 here, and I get and then once again I substitute the value of Z1 I obtained from this equation and substitute it here, So what do I get? Which is equal to R, and which is equal to Z3, because we call Z3, there is no section where the characteristic impedance is Z3. Z3 is nothing but RL. So my left hand side is equal to right hand side, and therefore all three equations are consistent. So that's the advantage that I get when I use this simplification. But there is one problem with this simplification also. There is one problem, there's one like mathematical problem given in the notes. We just go through that. Uh, what I want to show is this, because of this simplification, what happens actually. So observe this slide. Now here what I've done is I have used ADS to plot a 3-section binomial transformer, okay, that will match this 100 ohm load to the source 50 ohm. So there are 3 sections, n equal to 3 here. Now this problem is given in the notes, so go through this problem. I won't solve this problem in this lecture, but what I am showing you now is that the solution that I obtained, the mathematical solution for the 3 sections, that is Z1, Z2 and Z3 that I obtained, I actually designed a circuit where the impedances were like this. Okay, Z1 was 54.52 ohms, Z2 was 70.7 ohms, and Z3 was 91 ohms. Note that binomial, the nature of the binomial transformer, that Z's are all increasing, okay, and the gammas will be symmetric. The gammas will be symmetric, not the Z. The Z's will either be increasing or decreasing. And then I plotted the gamma in as obtained from simulation with the exact binomial formula. And you see that this red and blue lines are close, but there is a slight gap. Observe, this blue one is the exact expression for gamma in that I obtained from the binomial formula, and this red one is my gamma in that I obtained from simulation in ADS. They are very close, they do follow the maximally flat principle, but there is a slight difference between the two, and this is happening because of the approximation, because of that logarithmic approximation that I am taking. So I will end this part right now. In the next part, we will be covering the Chebyshev prototype function. So once again, just to repeat, we use prototype function, so that these prototype functions are simple algebraic equations which have a certain response, and we try to match the gamma in for our need to these prototype functions, and thereby obtain the values of the z's of the multi-section transformer. Now, in order to start discussing the Chebyshev prototype function, let us first talk about Chebyshev polynomials. The Chebyshev polynomials are a group of polynomials of various orders. So, for example, the first order Chebyshev polynomial is this, which is the equation of a straight line passing through an origin. The equation of the second order Chebyshev polynomial is given by the third order is given like this. Now in general, the nth order Chebyshev polynomial can be written in terms of the n minus 1th order polynomial and the n minus 2th order polynomial in this form. So you can verify that t3, for example, will be given by 2x times t2 of x minus t1 of x. Okay. Now a consequence of this polynomial is we can rewrite the nth order Chebyshev polynomial like this. So what this means is that if this argument is between -1 and +1, then the Chebyshev polynomial itself will be between -1 and +1. In other words, I can write that another way to write it is saying that if modulus of x is less than 1, then the modulus of the nth order Chebyshev polynomial will also be lesser than 1. Now let us, this was about the Chebyshev polynomials, but now suppose we plot the Chebyshev polynomials versus x, how will they look? So let me share my slides. So let us take a look at this graph. Here the x-axis is the x value and the y-axis is the value of the Chebyshev polynomial. As you can see, now these have been plotted for the various orders like n equal to 1, n equal to 2, n equal to 3 and n equal to 4. And you can see that these curves verify what we just saw right now, that when the value of x is between, or in this case say theta is between -1 and +1, and the Chebyshev polynomial will also lie between -1 and +1. However, note one thing, that there is a new feature called as ripples. For example, let us consider the n equal to 3 curve. Here this blue curve has this ripple-like feature. For n equal to 4, there is this purple colored line. It has two ripples. So that's one disadvantage of Chebyshev polynomials, that as compared to the maximally flat or binomial polynomials, which gave a perfect flat response, Chebyshev polynomials have this feature called ripples. And because of that, when we shall see when we build our input reflection coefficient using this Chebyshev polynomials, there will be some ripples in the passband. On the other hand, the advantage is that since we are sacrificing the very flatness of the response, we can obtain the same frequency response for lesser number of sections using Chebyshev polynomial. So that is one advantage. So coming back to, let us go back to our frequency response curve. Our frequency response curve was something like this. This is pi by 2. This is my theta m. This is pi minus theta m. This also, this pi up by 2 is also sometimes I call it theta 0. This is this point corresponds to mod gamma. This curve we know, we have seen this curve earlier also. Now here, if we could devise a function or a relation between theta and x, so that when theta lies between theta m to pi minus theta m, that is basically this frequency range, x will lie between -1 to +1. Okay? If we can devise such a method, then we see that the entire passband frequencies or the entire passband values of theta can be mapped to this -1 to +1 range of x. This -1 to +1 range of x, as you can see from this equation, forms a boundary. So the approach to framing the prototype function using this Chebyshev polynomial is to first map our this range of thetas to this range of x. Beyond this range, so this range of x will correspond to the passband, and within this range our gamma in theta will have a magnitude lesser than gamma n. So that is also something we have to frame. Okay. So we have to frame, as you saw here, that the Chebyshev polynomial allows you this facility that when mod x is less than 1, the value of the magnitude of t and x will also be less than 1. So our first mapping will be from theta to x such that this relationship is satisfied, and the second is that when t and x modulus is less than 1, my gamma in theta will be lesser than gamma n. So I have to form a relationship between gamma in and Tn so that when Tn x modulus is less than 1, my modulus of gamma in is less than gamma n. So it might not be clear what I mentioned just now. So I'll just show you the mathematical expressions. Let us say we take x equal to cos theta sec theta. Okay. You can see that when this equation verifies that when theta varies from theta m to pi minus theta m, this x varies from -1 to +1, or I should say it varies from +1 to -1, isn't it? For all other values of theta m lying between this range, theta m to pi minus theta m, modulus x will be lesser than 1. Okay, so this requirement is satisfied. This first requirement is satisfied. So henceforth, we will take our argument as this quantity, cos theta sec theta m. What about the relationship between gamma in and the Chebyshev polynomial? So the relation is given by gamma in theta is equal to a See, this relation, this gamma in theta, is related to this Chebyshev polynomial and as you saw, because of the ripples that are present, uh, the gamma in response will also have a ripple. So that is one property of this Chebyshev prototype function. So by the way, this is our prototype function. Okay. Now we have to still find out the values of this quantity A so that this relationship is satisfied. So how do we do that? To do that, we again follow the principle that we used for the binomial polynomial, for the binomial prototype function, which is that gamma in for theta equal to 0 is equal to gamma L. Okay, so now substituting this value here, we get gamma in theta equal to 0 is equal to A Tn sec theta n. Okay. So from here we get, now comparing these two equations, we get A is equal to gamma L upon Tn sec theta m. Now note that gamma L, which is given by this value, can be both positive or negative depending on the values of RL and Z0. Okay. Now substituting this value of A in this equation, we get gamma in theta is equal to gamma L upon Tn sec theta m Jn theta Tn sec theta m cos theta. Now at theta equal to theta m, we have gamma in theta is equal to gamma m. So this means that, this implies that gamma m is equal to gamma L upon Tn sec theta m e raised to gamma in magnitude is equal to gamma m. So from these two equations we can say this is equal to this Tn of 1. Tn of 1 is equal to 1, so this is nothing but modulus of gamma L upon Tn sec theta m. Now note that this quantity, this Tn of sec theta m, is always positive because sec theta m is always greater than 1. Okay, so because theta m itself is between 0 and pi by 2, so sec theta m will be greater than 1. So this, since this quantity is positive, okay, this quantity, that's why we have not taken any modulus sign here. We have just taken the modulus sign for the gamma L term. Okay, so now then you can see that this gamma m is nothing but equal to the modulus of A, the expression for A we had derived earlier, this one. You see, gamma m is nothing but the modulus of A. So then we can write this gamma in theta, gamma in theta can then simply be written as plus minus gamma m into e raised to minus j n theta Tn sec theta m cos theta. Okay, now here this plus sign, this plus sign, this one happens when RL is greater than Z0, and negative sign for RL lesser than Z0. Okay,